Hi everyone, in this segment we are going to be discussing the effect of resonance electron donation on acidity and basicity. So this is the flip side of electron withdrawal. Electron donation is going to result actually in destabilization of the conjugate base. So let's dive into this. Resonance electron donation in general is going to be indicative of lower acidity in the conjugate acid, and it will destabilize the conjugate base. When we have electron donation via resonance in the conjugate base towards where the acidic hydrogen is taken from, it will result in destabilization of the base, and that increases basicity because we are destabilizing the negative charge. Okay, so I do want to preface this video by saying that electron donation via resonance is a little bit more nuanced, okay? It might not be the case that immediately in Orgo 1 you are exposed to this. However, it is a very important comparison to electron withdrawal, and I find that it hones students' ability to more quickly identify resonance withdrawal effects and resonance donation effects later in their organic career. So let's dive into this. Here we are looking at three different phenolic compounds, meaning we have an OH attached to a benzene ring. So here are the acidic atoms. We're looking at oxygens bearing a proton, and each of those oxygens is directly connected to the benzene ring. What is differing between these structures is the substituents that are attached to the ring. On our far right ring, there is no group besides hydrogens attached to the ring. Here we have an OCH3 group, and here we have an NH2 group. You will come to know these groups as being electron donating groups, EDGs, electron donating groups. And phenol, the unsubstituted phenolic compound, has a pKa around 10. Note the pKa values here. This compound has a pKa greater than 10. Now I haven't provided a specific value, but we know it's greater than 10. And this compound here, its pKa would be even greater than 10. And certainly greater than the pKa value of that acidic hydrogen in the middle molecule. Here's how we know that. So each of these groups, the OCH3 group and the NH2 group, are resonance donating groups. When you have an oxygen or a nitrogen directly attached to a pi system, they will donate into that pi system. So the oxygen and nitrogen atoms are donating into the ring. So again, to look at the acidity, we can evaluate conjugate base stability. So let's do that. We are going to look at the conjugate bases and think about how the negative charge in the conjugate base is stabilized. So the commonality between all of these structures in the conjugate base form is that we have the negative on an oxygen. And in order to stabilize that negative, we have to resonate it around the ring, right? That is how we would stabilize the negative charge and accommodate the extra density that we have in the conjugate base. Now, the idea is your electron donating groups, your NH2 group and your OCH3 group, will be counterproductive to the stability of the conjugate base. All right, this is really important. So we want to stabilize this negative by resonating it away from where the negative is originating. However, this NH2 group is resonance donating towards our negative charge. So we have an electronic force pushing electrons this way, and that is going to destabilize our base. That resonance donation towards the site where the acidic hydrogen was taken from is then acting to concentrate that negative charge, and it makes it less likely that we get this nice stabilizing resonance around the ring. That's really important. The OCH3 group is also going to be resonance donating, so it also will destabilize the conjugate base here. Now, the idea is the nitrogen atom of the NH2 group is less electronegative than the oxygen atom of the OCH3 group. The nitrogen atom being less electronegative means that it is better at resonance donating. It's more likely to share its lone pair and resonate it into the pi system. So we're going to say that the nitrogen atom is more electron donating, which means that resonance into the ring is going to be more destabilizing comparatively to the resonance donation of the OCH3 group. That OCH3 group is less electron donating. So comparatively, this base is more stable than this one because in this base, the NH2 is resonating more effectively, destabilizing the base to a greater extent. Again, if this is less stable, it is unstable. Unstable equals strong. If we're looking at the base, the bases are basic forms. If this is stronger, then its conjugate acid is the weaker acid, the weakest acid in the series. Okay? And if we now compare the middle structure to this one on the far right, this negative charge is not hindered. It can resonate around the ring and we can stabilize it. There is no destabilizing electron donation towards the oxygen. However, in the middle structure, there is that destabilizing resonance of the negative charge becoming concentrated from the resonance donation of the OCH3 group. Okay? So I really, really want you to be aware of this. We have electron donating groups and we have electron withdrawing groups. And any type of electron withdrawing group, we're going to actually make a statement over here. This is important. Any type of electron withdrawing group, will act to increase acidity. Why? Electron withdrawing groups will stabilize the conjugate base. Okay? But electron donating groups, as we've discussed in this video, will decrease acidity. Why do they decrease acidity? They will destabilize the conjugate base. And the destabilization of the conjugate base makes it a stronger base, a less stable base. So as we go from left to right here, we have increasing conjugate base stability. And in this comparison, it's a function of this molecule not having the electron donating group, and this is the least stable because it has the strongest, most effective resonance donating group. So really articulate this to yourself, okay? This idea of electron withdrawal and electron donation, they are flip sides. And specifically here, we have talked about resonance donation. And in the last video, we talked about resonance withdrawal. Resonance withdrawal increases conjugate base stability and thus enables our acid to be more acidic. Electron donation via resonance decreases acidity. Why? Because it destabilizes the conjugate base.